So, okay, so as usual, we will start by recalling some stuff, and I will try to remedy some of the things that happened. Like last time, the end was a bit confusing, so I decided to kind of prepare it anew and maybe go into some more details. So hopefully, it will be more satisfactory and more kind of comprehensive. The part about the internal homes, and then we will finish this section with a star, and we will start the section which doesn't have a star, which means that it should be more down to earth. And we will read what we have solved soon. Once I find out which. This. Yes. So let's start by recalling and adding a bit of new details. Okay, so recall what we have done last time, or a couple of times ago. So we defined a supermanifold. Supermanifold M. And we define it to be a pair of a topological space with a sheaf of superalgebras. This is topological space. And maybe for later, let me call the global functions. Let me denote them by GL. So this is the sheaf when you evaluate it on the entire space. Global functions. And we also define what a map of supermanifold is. In some general way, which more generally you can apply to ring spaces. So it was a pair of data, it was an underlying map of topological spaces, and then there was some extra data like how to relate the sheaves. And then there was a proposition which kind of told us that we can do things more down to earth. So proposition. So this was due to latest and later also found in the book by Manin, which says that there is a one-to-one correspondence. On one hand, you can study maps between a supermanifold, okay, and this kind of model space, local model, and these are in one-to-one correspondence with a set of P even functions, P even and Q odd functions, odd global functions on M. So just as in ordinary geometry, you can describe a map by specifying how these how the coordinates here depend on M. And I will add a third thing, which I didn't mention before. This probably should go in the original statement of the proposition. Okay. And that there is a one-to-one, this may be useful to know, that the one-to-one map between algebra morphisms on the global functions. From the right, so yeah, global functions to M. And just to leave a picture answer, let me put it here as well. Okay, so these are equivalent data, and it's kind of clear how the map goes in one direction. Like if you have a map, you can pull back functions from the right to the left, which is this thing. Okay, and then what we did later is that we tried to define, or we talked about internal homes. So we said that you can instead of talking about homes, so maps, so these maps of supermanifolds. Okay. So these assemble into this set. This is a set of maps. So, and then we discussed how one can turn this into or how one can instead build a supermanifold of maps, which is denoted by the underline symbol. And this was constructing by this, by requiring that maps into that space are canonically isomorphic to m times n, maps from m times n to p. And if you recall, the product was again defined categorically in the usual way. But it is the thing that we don't think it can be. And as an example, we discussed that when you study maps from the odd line, I think we didn't call it like that, but this is the odd line into a, let's say, ordinary manifold. That's what I mean by not curly. Then this can be identified with a shifted tangent bundle to that manifold. Okay, so what I'd like to do now is I will formulate a couple of remarks which should make this second last point also this is underlined. We should make these internal homes hopefully a bit more concrete. So we start here maybe. So remarks. So let me start by saying, okay, so if you have, so we can consider a category of Z2 graded vector spaces or super vector spaces. Okay, so those are simply vector spaces that the objects here are Z2 graded vector spaces. Which is just this to say that that we have a vector space and it splits into a direct sum of an even and an odd part. And that's it. There is no further data. And the morphisms here, so maps, morphisms, category, are those for linear maps preserving parity. Okay, so even maps, even gets mapped to even, odd gets mapped to odd. And so here we can, okay, so what does the home space look like? So if you look at all possible maps between two given graded vector spaces, then, well, it has two parts. I mean, it's a linear. It's as you can see, there's a sum of, let's say, should I write this? Let me be kind of concrete. Let's say that this is all linear maps from even part to even part, and then there is okay, so in particular it's a vector space and it has these two components. Okay, so this is a vector space. And hence it's not really, it's not really super. So it's the analog of this a home which was not underlined. It's like we started with Z2 graded vector spaces, and this thing is not a Z. I mean, okay, it is trivially a Z2 graded vector space, but it's a silly one. It is more like an ordinary vector space. But you can again formulate the home in this an internal home in this category. You can see this. You can build a different thing, which is home underline, which will have now also a structure of a Z2 graded vector space. And this thing is simply all linear maps from V to W. And so if you want to decompose it, then it will have the same 2 bits as here. But it will also have 2 more, because it will also allow you to go from even to odd, and from odd to even. And this thing is now naturally a supervector space again, as I took a vector space, where this thing here is the even part, and this thing here is the odd part of it. And the way to remember that is, this is the thing changes the parity. It goes from even to odd, or from odd to even, so that's why it has internally a sort of odd character. And this is even. I think this is maybe an easy way to illustrate these internal norms in general. So now I want to do something similar to the, and also notice that the even part of this is now a Z2 graded vector space. And also notes, it is noteworthy to see that the even part of it is really the normal home. The home underlined, W, and then even part of that is really the ordinary home. So these internal homes, you can see them as, sort of having like some extra stuff that allows you to change some parities and things. So let's now do the same thing for supermanifolds. Let's go back to supermanifolds. And let's make a sort of maybe silly but very concrete calculation. So let's look at this adjunction, this kind of natural isomorphism, and let's take P to be this kind of simplest model space that we have, the RPQ. So let's calculate what this is. Or let me first write the adjunction. We want to understand what this guy is. And the way we do that is that we calculate the right hand side of this adjunction, which would be m times n into RPQ. Okay, so, and here I will be a little bit, okay, let's say, this derivation here is going to be a bit heuristic, because I will kind of ignore the infinite dimensional troubles. So heuristic / cavalier, I hope that's a word, with infinite dimensional spaces. Just to give you some feeling of what is happening. Okay, so what does the proposition say? So this is kind of a technical tool. So the proposition says that this is the same as the second. So let's calculate the right hand side. By proposition, this is the same as having a bunch of functions. So this is the same as having P even functions and Q odd functions. In here, on the product, and on the product, no. Okay, this is where I'm being a bit heuristic. So I will say that this is, I will treat the functions on the product as this. It really should be a completion of this. Maybe like completion, whatever. But heuristically, just the tensor product of these things. Kind of. Okay, but now both of these things are superalgebras. Okay, both of these things have multiplication and they have this grading. And so we know what even things in here are. So if I continue here, let's say, here. So what are the even things? So we need to P even functions, and P functions in. So let's write explicitly what even here is. So even means that I either take it to be even here and even here, or I take it to be odd and odd. See, so it's this, and then and q functions in, and now the complements of all and even, tensor all and odd, plus the other way around. All and odd, okay, I have more space, sorry. All and even. It's still visible in the word file, surprisingly. Okay. Okay, so we just spelled out what the product thing. Okay, and now I want to go back. So let me write the. Okay, so here is where everything a little bit heuristic is not too bad. So let me call this thing V. This is an even. This is a vector space. It's very big. It's infinite dimensional typically, because these are functions on some supermanifold. But let me call it V. And take that before with it's infinite dimensional, just for the heuristics. And this thing is an odd thing. So let me say that this is a parity shifted vector space W. Okay, yeah. So, okay, and then I want to, when I claim that, then I can equally well write that this is the same as Holmes from M. Okay, now here I have to be careful. Okay, so I want to go back and I kind of want to reformulate stuff in this way. So okay, so I want to use a proposition kind of going backwards. So imagine that this would be a finite dimensional space like R3. And this is, yeah, I have p elements in there, so it's the same as if I would take this thing and I would take it p times and then also dimension of v times. So it's really, I'm taking p functions in here, sorry, p times, okay, let's say this has dimension v or something, dimension n, maybe, or we have n, okay. Well, so imagine this is 3-dimensional. Then my claim is that the first part is the same as having 3 times p functions in here. Make sense? Does it make sense? Oh, because it's a tensor product. Yes. Okay. Yeah. So. Okay. And so if I want to use the proposition backwards, and the proposition supposed to tell me that there's a proposition here that I need to take. The number of even functions that I have here should be equal to the dimension here. So, okay, so, okay, let me write what I want to say and then let's try to see that that's the thing. And here there is P of those. Here there is Q of those, here there is P of those, and here there is Q of those. So I sort of take the stuff and relabel it. Okay, so what does the second line? If I now want to use the proposition and go from here to here, so I should specify. I'm going backwards. I need to specify some number of functions here. I need to specify as many functions as is the even dimension of this. And the even dimension of this is the dimension of v times p plus dimension of w times q. Okay, that's the size of this even stuff here. So I need to specify this many. This is the size of this dimension. So I need to specify this many even functions, and that should be precisely what we have up here. So I specify p times dimension v functions here, but I also need to specify q times w functions in here. Okay, so I just reorder the things. And the same here. And I need to specify the number of odd functions. They should equal the number of the dimension of the target here. And so, how many odd functions do I need to specify in here? I have here odd and here odd on M. So I need to specify this many times P. That's this. And I need to specify this many times Q, which is this thing. Okay, I leave the if it was not clear, then you can think of it on your own. Here it's kind of like a silly argument. I'm just counting things, so it's not really naturalized. It's just I'm just writing set equations, or well, sort of. So anyway, okay. But then the last step would be to realize that the thing that I just wrote, this is the same as morphisms from M into the global functions. Okay, everywhere should be global. Okay. Yeah, let me just ignore that. There should be global functions everywhere, unfortunately, but I don't have enough subscripts. So imagine that global function, global. Anyway, here times RPQ. Okay, so I collected the things back, and I say that okay, you have this super algebra. It has.
So it should be ON, right?
Sorry.
Should be ON.
Yes. Thank you. Yes. Right. Thank you. Perfect. So yeah, this thing is what I previously called V plus parity shifted W, and you see that this thing I can equivalently write that this is RP plus parity shifted RQ. So as a super vector space, it's just a product of those things. Hopefully that's correct. There's P copies of V, P copies of shifted W, and vice versa. Okay, so last thing to say. So I'm saying, okay, so what is this object? This is a super vector space. Or is it, I mean, it has Z2 grading, and it's a vector space. So I understand that super vector space is a super manifold. Z2 graded, that Z2 graded vector space as a super manifold in the usual way. Okay, so we have like A plus B vector spaces. Then you can see this thing as what we formal. So this is kind of a okay, you can say that this is kind of a bundle over. You have a bundle over V, and you parity shift. Sorry, over A, and you parity shift that bundle, so that the fibers become odd. E, then you take this parity shift to E. That's okay. Maybe unnecessarily complicated way to say how does you see this supermanifold corresponding to a supervector space. Just before I introduced this notion, that's why I wanted to connect it. A parity shifted vector bundle. If this is confusing, feel free to forget about it. You know, anyway, this is anyway the result. So the where is the sponge? So the result is that we now know what the internal home is for maps valued in RPQ. Any questions or comments or complaints or Did I hear a question? No? I still need to erase the other board. Let's just remember the result. So these internal homes are interesting spaces. I mean, depending on how the schedule goes, we might not encounter them really later on. It depends on if yes or no. But in physics, they pop up in various places. One of them is when you want to use the so-called AKZ construction. Or AKSD construction, maybe. Which tells you that if you have a map of two supermanifolds, then the mapping space is also a supermanifold. And it does a bit more, but that's kind of part of the statement. So we need to use this in there. Okay, really no questions?
Okay, so I might have a question about the even-dimensional thing.
Okay.
Are there ways to like do this mathematically precisely?
I think so. I mean, just by brief. I mean, I'm not an expert on this kind of aspect, but just by brief googling, I found some like people formulating it in the Fresher world, like Fresher supermanifold.
Okay.
So it should be perfectly doable. Thanks. Okay, so what was the conclusion of this calculation? So if you're interested in maps, let me rename n to m, just because m is more basic. So we showed that, showed on the level of sets, or like on the level of calculation, counting degrees of freedom, that this is the same as, the supermanifold this is simply all functions, all global ones, tensor with RPQ, M. Okay, now let's draw some conclusions from this. So, first thing to see, I realized maybe the last line they erased might have been a bit handy. Okay, sorry. Because I wanted to point at it. So, sorry. Let me rewrite the last line. And then there was this calculation that shows that this is the same as P of these guys. Q of these guys. Q of these guys. Okay, so one thing that we see here is that if this is supposed to be a supermanifold, then we see what the underlying base of that thing is. It should be the kind of if you remove away the old stuff. So the old stuff here is really given just by these V's and W's. And that by the proposition that's precisely the ordinary home. If you have a home of okay, let me just say that we stick to what we have. So, and you take the reduced space of that, then this thing should be the ordinary home space. And they should be true more generally, even if you don't map into RPQ, but into some more general stuff. Okay, so the base is just as before in the vector space example with supervector spaces. And okay, then one more thing. This is just okay. So occasionally people say, so now that what happened here is it seems that we have sort of like a generalization of this proposition. We now have that if you forget a moment about the subtleties here, you see that now to every coordinate in here you are assigning a function. Before we only had that you assign an even or odd function depending on what the parity of the coordinate was, whereas here you assign all the functions. So it's kind of like if this was a set, then its points would be kind of that is need to specify. If I want to write like one-to-one equivalence with what we had before, analogous to the proposition before, and I could say that map the elements in here are one-to-one with p plus q functions on m without specifying parity. Of course, this really doesn't make sense as I stated it because this thing is not a set. It has some underlying real space, and then there has some fluff, some odd fluff. But maybe at least mention is that sometimes it might be useful, but it also might be confusing. So occasionally, people would say that would just say that you take these functions, these coordinates here, which I think we call them y and eta, I guess, last time. So you say that this thing is now an arbitrary function on m, and same as this one. Okay, so this would be kind of the analog to what we had before, where you only here require this is an even function and this is an odd function. Or you can say that something like maps like this, they correspond precisely into this. If you want to write something analogous to the proposition, you can say that this corresponds to picking up p plus q functions on m. But again, you should be careful with this because it's not really rigorous. It's not really strictly speaking true because this thing is not a set. So the right hand side is obviously a set. This thing is not. So you have to be careful when you make statements like this. But maybe for some intuition, yeah, actually that might be actually a questionable thing. Maybe this is not really useful to think of it this way, but anyway, I feel that you can say this sometimes. Okay, so careful. Because this thing. Sorry, I called it maps. Why did I call it maps? Oh, no one complained. It's not a set. I would underline not, but then it would be confused with the inter-home. Okay, but what you can say, at least, and the stuff that makes kind of sense is that, so say if ya and eta alpha are coordinates on RPQ, and okay, here is the final notation, so EA and FM are basis elements, again, heuristically speaking, of the algebra of global functions on M. Okay, so I have that space. I look at the, I take coordinates here, and here I take the basis of all functions, which are different things, right? So here you can, if you like, you can think of Fourier on a circle. So you have like the basis of e to the I m phi. Where does this go from? Well, minus infinity or something. Right? That's a basis in a suitable sense. So, okay, and if you have such a thing then, and the home space has naturally the coordinates, this thing has coordinates, and labeled. Okay, this is for people. Okay, maybe this is preferred for by people who like indices, but I think it is maybe illustrative. Okay, because how do you know if you okay, I will say that in a second. And these things are even, and these things are odd. So although this thing is not a set, it is a super manifold of infinite dimensions or something. So it is not a set, but you can still talk about coordinates. That's a meaningful thing. And coordinates that are even and odd, then the claim is that if you choose some sufficient trivialization or like coordinates here, then you can describe them in this way and precisely get these sets of even and these guys which are odd. While if you would have non-internal home, but the ordinary one, then this would be these are the coordinates of the normal home. Okay, is that okay? And now maybe to comment on the indices, like an element in here was an assignment of, we picked p even function here. And q odd functions here, and what I'm doing here in this coordinates, I'm just expanding these even and odd functions in these bases. That's why I have two indices there. Okay, moral of the story, it's not a set, coordinates are meaningful though, so you can write coordinates. And of course here I forgot to say that these are the even and these are the odd, but perhaps you understood that. These things. Okay. With that out of the way, any questions? No, we'll do the fun parts. I mean, more fun. Slightly more fun.
Is there more fun than this?
Well, yeah, you will see that. Very good question. I know it's hard to. Okay, so just to close the whole section, let me tell you some cool facts. But before that, let me give you a dry definition, so let's just to get it out of the way. So we talked about. No, actually, no, sorry, that's the end, right? Yeah, that's the end of the section. Just the papers are being disordered like this. Any questions for this part? This should conclude the confusion, well, or maybe not, but it should address the potential confusion that I did the other week. Even if there are no questions, we will see a cool example of this in a second. So let me start a new section. It should go back to Earth, down to Earth. Supermanifold coordinate approach, we call it. So you might think that coordinates are not a great thing to do. In ordinary differential geometry, it's typically much more instructive to work in like the abstract approach, but in supermanifold it seems to be particularly convenient to work in here. But underlying that, it's good that we've covered all this abstract ground so that you can have some sort of intuition of what's happening, and you can make the statement more global if you wish. So the sentence I prepared to say was that now that we have developed the abstract approach as well as some intuition, we will proceed to work mostly in coordinates. I won't write that down. So let's now continue a bit more, and essentially the thing I'm going to say, you can formulate them again in a more formal and abstract way, and like more global and coordinate independent. But for what I want to say, I will just proceed by doing things in coordinates now, and you can assume that you can imagine that there is like a similar way to make things more global, but it will be more convenient to just proceed in coordinates. Let me talk briefly about vector fields. So how to define vector fields? So far we know what manifolds are, what supermanifolds are, what maps of supermanifolds are. So what is a vector field? So an abstract definition could be that an even or odd vector field, it's two definitions in one, even vector fields and odd vector fields. An odd vector, even or odd vector field is an even or odd derivation of the algebra or superalgebra of, in this case, let's say global functions on M. So what does this mean? I.e., it's a linear operator from this space to itself, which satisfies such that if you act on functions of concrete degree, then you change or not change their degree depending on whether it's even or odd. Okay, so these things will denote parity. The absolute value as before is parity of the corresponding object. And V was an even vector field, it's 0, if it's odd then it's 1. So this is really like mod 2. Z2. Okay, so this is 1. This is what it means for thing to be even or odd, but we also want it to be a derivation, so say and it satisfies the derivation property that if I act on a product of two functions, then I get the usual thing, and then I get a causal sign if I act on the second guy, because I need to exchange V with F. I need to multiply this with this causal sign. Okay, maybe let's say mark. Vector fields carry a natural bracket. If I have two vector fields of definite parity, then I can define V W minus usual causal sign. You remember the causal sign, right? Whenever you exchange two objects, you need to account for -1 to the product of their parities. Whatever those objects are, if they're be them vector fields or functions or operators or whatever has degree. Okay, so this is the general definition that works even more generally, even if you wouldn't work with supermanifolds, but some non-commutative spaces. I mean, some general algebras that you can talk about this. Now, in local coordinates, which is what we are aiming for now, let's say we have local coordinates, these ones which are even, x, and some size, alpha, which are odd. Then vector fields will simply look as follows. So you can imagine that some coefficient functions depending on the coordinates, and then there will be partial with respect to xi, and partial with respect to xi alpha. Okay, so now a few comments are in place. So one thing that I did not mention here is that this property here. So these are so-called left derivatives. You can see that because the stuff naturally acts on V kind of attacks the things from the left. So this condition, well, okay, anyway, this is called the left derivative. I won't. So it's common in the literature that people introduce also right derivatives, which would kind of act on things on the right, and the corresponding sign would be different. I don't use those, so you can consistently get away with just these types. So everything here will be a left derivative. So in particular for experts, like typically the B Boston bracket is written in terms of left and right derivatives, but you don't have to do that. It works just as well. Okay, so that remark out of the way. So what do I mean by? So this kind of coordinate approach that we are going to develop, it's really just sort of game where you have these kind of ingredients, you have x's and x's, and you will be throwing various symbols here, like this symbol, which sometimes I will just call it partial xi. Okay, so I don't have to write that much. So you just imagine that you have some functions of x's and xi's, and then some symbols like this. And so what is the meaning of this symbol? So this is the usual partial derivative with respect to x, right? And this symbol is defined. So this is a vector field defined by the property that if it acts, okay, I'm going to write something that's very silly, but okay, if it acts on x's, it gives 0, and if it acts on xi's, then it gives a Kronecker delta. And because these things are there, satisfy these derivative properties, then you know that they are determined on what they do on coordinates, because then you can determine what they do on products of coordinates. So you didn't have to specify what they do on the generators of the algebra, on the coordinates. So I'm saying that this vector field is defined like this. If you would work with right derivatives, then you can also define right derivative with the same equations, but then it would extend differently to general functions.
So usually you can say that if you have product of xi's like that and the partial derivative, so you look that your xi index alpha is commuted over to the left and then cancel.
Yes.
The right would be
yes, the other way around. Yes.
Yeah.
Yes. So yeah. In other words, if you imagine that you have an expression something like so yeah, this is Bernier saying that if you have like let's be concrete, you have like psi1, and you would have some expression, then you would have psi2, psi3, psi7. Okay, this is very random, but I'm sorry. Psi1, psi0, no 0 is not there. 4, thank you. Right. So to calculate such an expression, what you do is that you use the fact that this anti-commit, so you move this guy to the front, you pick up 3 signs because you have to pass 3 guys, and then you remove it. That's what it means that I use these defining properties and I use this so this would be simply minus the thing with gamma 1 removed. If you would work with right derivatives, then this would be well the same because you would move this thing. You would need to move it to the right and then remove it. Let me put maybe some other guy here, psi 5, to emphasize that this is different from the right one, which we won't talk about anyway, so that's fine.
Yes, I can have a question.
Yes.
So, with the vector fields, a vector field is always even or odd.
Yes.
Right.
Yes.
So there's some restriction on the degree of the functions f and g.
Okay, so.
It's not true that vector field is even or odd. The
No.
same way you can have a sum of an even or an odd vector field, which is that is inhomogeneous.
But you can always split
Yes.
Yes. There's a subtle difference of whether I want to talk about those two things separately or if I allow general combinations. And here I probably want to allow general combinations. So I would say that the vector field is not just so general vector field would be a direct sum of these two guys. So I allow non-homogeneous, is that the word? Yeah, non-homogeneous things.
So is it still a linear operator if it's inhomogeneous?
Yes, because they define it by linearity, so it extends linearity from these things. So if you would have like a vector field which is even and one which is odd, then you would act on a function which is of some parity, even or odd. Is that true what I'm saying? Is it good?
It depends on what you want to say.
Yeah, sorry, they're both linear operators, so linearity is still fine. Okay, okay. Sorry, yeah.
Thanks.
Thanks. No, that's a good point. This is a bit, yeah. But yeah, here I want to allow. So let's say general vector field. Although it's kind of true that I won't really need. All of them will be homogeneous always. So let me maybe not say that. But okay, so I could do that. I could just say the general vector field is a direct sum of those.
You can say that it is even if f is even and g is odd, and it's odd if it's the other way around. No?
Say again, sorry.
You can
Oh,
say-
I mean here.
Yeah, you can say that this vector field is even
Yes.
if f is even and g is odd,
Yes. Yes.
and the other way around.
Yes. Right. Okay. Is it good? Thanks. Perfect. Okay, so okay, so I had a beautiful example prepared. To take R02. I mean that example was essentially covered here, but yeah, it was essentially covered there. So no example. This was example. Okay, now comes a real example. Where finally we will see some cool stuff. Although if you've seen this before, it's not. Well, it's best if you haven't seen it before. The drawings thing. Is the time? Any questions? Did they already pass with it? No. Okay. Thank you. It doesn't seem to be doing much. Okay, so now the kind of one of the most fun examples of supermanifolds that you can think of is the parity shifted tangent space to an ordinary manifold, let's say. So this is a manifold. So this is the parity shifted. I guess there's a hyphen. Probably. Tangent space. Okay, so this is just the thing we've done before. You take a vector space, take a vector bundle, and you assign the linear coordinates of the fiber an odds parity. So this is a special example of what we've seen before. And what are the global functions? Well, either you can figure it out in coordinates, or you can remember how we actually define these things. That the functions of this were the exterior power of the dual of this thing. So this was the section of the exterior power of the dual. This is nothing else than differential forms on M. Okay, so first moral, the functions of this guy are differential forms on M. And now, okay, if you look above, let's not go into coordinates yet, but if you look above, so do you see any interesting vector fields on this thing? Okay, so vector fields again are just derivation of the superalgebra function. The superalgebra functions here is the differential forms. So does anyone see some interesting vector fields living on this place? Only people who don't know should answer. Which is a sort of paradox, I guess. It's only people who really don't know. Oh, anyway, you know what? So, any interesting vector fields in here? You can do it. Okay, even people who know can say. They're correct. So, they're differential. Is a vector field. What is the parity of this vector field? It's odd. It changes it increases the degree by 1, so it changes the parity. So this thing is an odd vector field on pi tm. Okay, any other?
Any derivative with any vector field.
Very good. So for all vector fields, Lie derivative also satisfies that thing, and it is an even or odd derivative relation.
Even.
Thank you. Even. Okay. You can see what's going next. The interior derivative, yes.
Yeah.
Which is even or odd?
Even.
Or odd. It changes the degree.
Oh,
It
right.
lowers the
Yeah,
degree.
sorry.
Okay. Does anyone see any other vector field that lives in here? Maybe one which doesn't even require a vector field on M. There's at least two that I can think of.
Is it the order vector field?
Yes. And okay. My choice was the other one with the 0 1. Yeah, the order vector. So there is another vector field. Let's call it Euler vector field. Let's call it E for unknown reasons. So this is a vector field that when you act on a form, which I now should give it a name. So let's say omega. Let's say this is a P form. Then it returns -1 to P to the degree of alpha. Sorry, no, it doesn't. Sorry. P times alpha. Yeah, okay, thank you. That was of course intentional. And this is a vector field because if it satisfies the. So is it even or is it odd? If it is a vector field, so that's only this. And what is the parity with? Even. It doesn't change. It starts with a P form, it ends with a P form, and multiplied by some number. This is even. And why is it a vector field? Well, if you act on the product, which is just the same as the product, then is this thing the same as acting on the first thing plus, since it is even, this factor goes away. So let's just down to beta. Is this true? Yes, it's true because the degree is additive. So if this was degree P and Q, then this thing returns the same thing with P times Q. This thing returns P. This thing returns Q. So P plus Q. Yeah. So okay, yeah, you can see that. You can. This is a P form and Q form. This thing returns P plus Q. Here it returns P. Here it returns Q. So beautiful. Okay, so now what does this look in local coordinates? So what are natural coordinates on that thing? So pick ordinary coordinates on M. M, coordinates, let's say, xi. And these things will naturally induce these induce coordinates on the tangent bundle. And these coordinates will be x and something, let's call it xi. Okay, so if you specify a vector field, if you specify coordinates, then you also have a natural coordinates there which will correspond to the coefficients of partials. Right? So naturally you have a coordinate system here. And when you pass the pi of the m, what you do is that you take the same set, but you declare these are even, and these ones are odd. And you can see that the correspondence with forms is simply that if you start with a P form, it's beta, and you can write it as some coefficients, dxi, dxj, and the way you would write it in our language was in the supermanifold language that you could just replace these dx's by xi's. Okay, that's how correspondence works. And they both dx's famously anticommute with each other, and so do the xi because they're odd. And now we can also write the vector fields in coordinates if we want. So even if we don't want, I will write them. So how do you determine? So how do you write this thing in coordinates? So what are the coordinates? X and psi. So this thing should be, it should be some stuff partial x plus some stuff partial psi. So how do we determine what's in there? Well, we look at what it. How do you determine the coefficient function of the vector fields? You look how this acts on the generators. How it acts on axis, then you know what this bit is, and how it acts on xi's. So how does this d act on the axis? Well, if you hit d with xi, well, then you get dxi, which is just our psi. Okay, so it's a bit tautological written like that, but it's, you know, this psi, you should really think of it as psi is the same as dxi. So if I apply d, it transforms x into psi, which means that the coefficient here is just psi. And how does this thing act on psi? Well, remembering that psi was already d of something, this thing is 0. So this thing is not there. So this is the Derham differential written in the coordinates. What about the other guys? So what about the lead derivative?
Why was the xi 0? Why, how did you
Because
argue?
psi was dx.
Okay, just like that.
Yeah, I'm sorry. So if you want, okay, I mean I did it a little bit fast and a bit confusing in writing things like this. But I mean, if you the way you do it is that you look at what it does in here, and then you use this transition and you replace dx. In the end, you replace dx by xi's, and you see that. Yeah. But yeah, it's a good point. I'm doing it a bit fast. What about the lead derivative? So if you take lead derivative with respect to a v, let's say, on the function x, well, then this is just the vector field acting on x, which is just v of the coordinate u of I, which depends itself on x, right? This is a given vector field, which is in general position dependent. Now, how does this thing act on dxi? Sorry, xi. I'll determine that. It's okay. Okay. I don't know how to. Okay. Let's write it like this. So what is this? So you know that d commutes with the lead derivative. So this is just the lead derivative, and then followed by d. So it's the same as above, but the extra d. And this means that this is partial j vi of x followed by dxa. So maybe more coherently with what you were saying, I kind of did the calculation in terms of x and dx. I get something, and then in the end I translate it into our language. You see that the lead derivative vector field, it takes x into vi. So this is vector field. Removes an x and replaces it by vi, and it removes a. And how does it act on xi's? Well, it removes the xi, and then it multiplies it with this nonsense, and that nonsense is partial j vi x, and then there is another xi there, xi j. Does it make sense? Do you see confusion? Does the indices not match? Okay. No confusion. Since I brought so many colors, now the I. The I is simple because what does the contraction do? If it acts on a coordinate function, it just produces 0. And if it acts on d of xi, what does it do? Well, it's simply the v on xi. Right? Yes. Which is vi. Which means that v will not have a partial x part because it kills x's, but it will have a partial xc, so this is simply vi on partial xi. Is that right? Yeah. Okay. Now the order vector field, that's the most funny one. Well, let me just write it. The order vector field is psi I partial psi I. You can check that one. Okay, and this is a brilliant place to stop. And let's make a break for until half. Okay, welcome everyone. Right, so
Can I ask something?
yes, please.
So we didn't write down xi del psi I as a possible vector field,
Yes.
and xi is not a global vector field, so it didn't really fit into the.
Yes.
Is that a?
That's a very good question. I think that thing is not coordinate invariant. Like if you would change coordinates, it would change.
Yeah. Okay. That's the one.
Yeah. And while the things that I wrote, they don't. If you choose different axes, it still takes the same form, and you know that's true because the construction didn't use it. It was just
Yeah. We wouldn't change linearly that one if you change coordinates. That's the
yes. I mean the other ones would not change at all. They would not just change. They would like. They have a different coordinates. They would be equal.
Yeah. Okay.
Yeah. But yeah, this one is different. It's yeah.
Okay.
Yeah, the expressions that I wrote for the other ones were also not global because they had x's in them, but they are coordinate independent, so they will patch naturally. But no, very good question. Yeah, in terms of indices, it looks fine, but it doesn't behave well with respect to change the coordinates. Yeah, that's a very good point. We could have mentioned that. Maybe it can go into lecture notes. Okay. So what have we learned? So we learned that if you take these functions on this phi tm, and they are differential forms. Let's say I don't know, global. There are differential forms on them.
So didn't you want to also express the Euler vector field?
What I did, didn't I?
Did you do that? Sorry, maybe I just missed it.
I did that, right?
It was one of the colors.
It was psi I d psi I.
Okay.
Psi I partial psi I.
Okay, thank you.
Yeah, it was a little bit hidden.
Alright.
Okay, so we now know that there is a space, namely the shifted tangent bundle, and the functions on it are differential forms, which is a cool thing to take away. There is one thing you should take away from this whole semester, could be this one. But there is more cool stuff that you can do this. So let me formulate it as a remark. And again, let me formulate the statement. So I won't prove them. I will just let you know that if you have given a supermanifold M, you can study maps from that supermanifold to itself. You can ask them to be invertible. So one can define diff M. So this is maps from M to M, invertible in suitable sense. And this is a group. Okay, it's not a supergroup. It's a group because it consists of maps. So this is invertible maps. Okay, from M to M. I'm being a bit cavalier with like technical details such as infinite dimensionality. Although I didn't say anything yet about that. But anyway, this is you can give this a sort of. You can imagine this could have like some sort of manifoldish structure. But the important thing is it's a group. It's not a supergroup, it's a group. It doesn't have any odd directions. It consists only of maps on or it's like a part of home space, not underlying home space. And this thing is generated as a group, generated by even vector fields on M. So vector fields of even parity. That corresponds to the fact that it's just the even part of the thing. But one can also define, let me not discuss how and why, etc., but can also define a supermanifold of different, I don't know how to call them, so I won't call them anyhow. I will just put a bar here, underline. Hopefully that's understandable. So I'm just saying that similar to before, you can find a different thing, and this thing is a supergroup. Or really supergroup. I didn't define what a supergroup is, but on the level of, if you imagine it some sort of, in particular it's manifold with some operations. in this case a supermanifold. So this thing is really a supermanifold. It has some odd directions, and its basis, its radius space is this diff m, the ordinary one, but it has some other stuff. And if you like, on infinitesimal level, you can be more concrete. You can say that this is generated by all vector fields. Even and odd. Okay, so example. So let's look at what the maps from the odd line into itself are. Odd line being a great space because it has many strange and curious properties. So what are the maps from this guy to itself? So let's call the coordinates here theta, and here I guess theta prime. So there is one odd coordinate, and if you would, let me do the ordinary home first. So if you would have ordinary homes, then the proposition tells us that to study what these things are, you need to take this thing, which is an odd guy, and you need to assign to it an odd function in here. Odd functions here, there's not that many of them because the algebra here is only generated by one single odd thing. So these things are simply the assignment where you say that this thing is some number times theta. Okay, this is a real number. A is real. So this thing is the reals. So is this notation clear? Is it just like I'm using the proposition here to say that this is in one-to-one with assignment real thing, function here, and the function here general odd function looks like this. And how many of them there are? There is the freedom of having one A. That's why I want this A. They are. Okay, so now if you do the underlined home, and here I will use one of these interpretations from the previous remark. In this case, you can easily say that I will use one of the statements from before, which says that here you now take your coordinate here and assign it a general function. Okay, so this thing consists of a general function, and the general function is more than A. It can look like A theta plus B, where those things are real numbers. Oh, actually, sorry, no. Let's not say that. Because here I'm using one of those dubious interpretations of like, but anyway. Well, sorry?
Why can't we say they are real numbers?
Because this is an odd thing. So the way this matches with the previous discussion was that this thing is a super manifold.
Ah, I see.
And it has one even and one odd coordinate, and this is the even coordinate. And this is the odd coordinate. Maybe more coherently before I should have, but let's not say this, and let's just say that this A is an even coordinate. Okay? This is a little bit of an abuse of notation, but the result is correct. Like that all such maps, they are parameterized like this by some number, so you can call the number a coordinate on this space. Right? On this space. And what I'm saying here is just kind of a slick way to say that, and to translate that kind of imprecise statement that I said before, that you assign to coordinates here an arbitrary function here. So I wrote that. It's a bit imprecise, but it gives you what is in this case, correct? You can do it if you want. You can beat into it with rigorous steps that we did before, but you will get the same result. That there is one even and there is one odd coordinate. You can even use that last remark in the what I said before. If you pick coordinates, if you pick a basis of functions, then you will end up precisely with this result. If you don't like the way I have it here, but yeah. So this thing has dimension 1 + 1. Should I? Okay, maybe if this is confusing, let me also say in terms of that remark that I mentioned before. I said that if pick coordinates on the target, which is theta, right? And if you pick a basis of functions on the left, functions on the left were simply a theta plus b, So the basis, so this was what before we called E, and this is what before we called, this is what before we called F, and this is what we before called E, which before carried in indices A and M. And if you remember that statement, it was like the coordinates on this mapping space, they will carry an index from here and one index from here. So there will be precisely one corresponding to the combination of this guy and this guy. That should be this thing here. And there will be another one coming from the coordinate here and the coordinate here, and that's the second thing. So I'm redoing the same thing in terms of the last part of the proposition of the remark that we did before. You want to see that more concretely? I was hoping this might clarify things, but okay. Yeah, it takes some time to wrap your head around this, but is the idea clear? Okay. Anyway, where are you with this? It works. Okay, so this is the home space. So this thing here before had dimension 1 real dimension. This thing is dimension 1/1. And now let's do diffeomorphisms. So again, without proving it, let me just say the diffeomorphisms from this guy to this guy, which is a special case of invertible maps here. Then the claim is that they are kind of the same thing, except that you impose that this first term is invertible. This is invertible. Because you want to be able to pass back, you know, that kind of makes sense. Again, I'm not proving this is just like because I want to state the thing that comes after, which is pretty cool. Okay, so the moral is that this is a group, so a supergroup, supergroup of dimension 1/1. Just as in the ordinary case, you would have like, I don't know, general linear group has the same dimension as like all linear endomorphisms. So whether it's invertible or it's not, it has the same dimension. Here you are just removing some like bad locus where A equals 0. Anyway, this is a group. It has one even and one odd dimension. And maybe to make it a bit concrete, we can say that this is again generated by some vector fields on this guy. By all vector fields. So if you find this global interpretation confusing, then we can think about vector fields, which is more doable. So what are the vector fields that live in here? How many there are on this space on R01? If we take the theta coordinates.
There's one even and one odd up to multiples.
Yes, so there is partial theta and there is theta partial theta. And this one is even because you see that you remove an odd coordinate. So I mean this operator is odd because it removes something odd, so it's odd. Multiplying it by odd is even, so this thing is even and this thing is odd. And those are the two things that generate together this supergroup of dimension 1/1.
Shouldn't it be partial A and partial B? But A and B are coordinates here.
They are coordinates on those things will be coordinates on diff.
Oh, sorry. So these are okay.
These are vector fields on R01. Yes, sorry. Yeah, a good point. Now I'm talking. Yeah, now I'm saying that you have a space. You can imagine that you have diffeomorphism on that space. So those are generated by vector fields on that space, and they are generated by these guys. And okay. And now the punchline. One of the punchlines. Is this clear in some sense? If you don't like the global interpretation, just think of the vector fields there. They're kind of easier to deal with. The claim is that you can make this more global if you integrate them. But anyway, I'm not describing the theory of integration on supermanifolds, so that's why this is a remark. So what we've seen before, if you take differential forms, you can see these as functions. I'm just writing what's above. These are functions on some specific manifold, which is pi of Tm. So global functions on pi of Tm. But what is pi of Tm? Remember the proposition, these are global functions on Tm, are pi Tm, but pi Tm was precisely functions. Pi Tm was the internal home from the odd line into M, right? This is the proposition we showed the other day, and I recalled at the beginning. So this I just rewrote what pi Tm is. Pi Tm. So now forget the fact that this is supermanifolds. Imagine that this would be normal stuff, normal manifolds or something, or sets or something. If you have a space of mapping, if this would be manifolds, so if you have like maps of manifolds, I don't know, A and B, natural manifold. So if you have a diffeomorphism of A, then diffeomorphisms of A act naturally on the home space. Is that right? They can precompose any map from A to B with the diffeomorphism of A. Okay? This thing carries, actually it's a right action, for A, B manifolds. The diffeomorphism naturally acts here, right? So if you have a diffeomorphism phi and you have a map F that goes from A to B, you can form a new map phi, I don't know how to denote it, phi star F, I guess. And this map will be given by F but decomposed with phi. Okay? Diffeomorphisms naturally act on mapping space. Similarly, diffeomorphisms of B would act on them. So if you now carry it here, then you will see that what is the analogous thing that's happening here. We discussed the diffeomorphisms of the odd line, and now we have a map from the odd line. So, okay, again, okay, I'm just writing this. The claim is that you can do a similar thing here. Again, proving that just by analogy. This thing on the right, this thing acts on the home R01 into M. So this is a supergroup action. Again, I didn't give you the formal definition. You can imagine it's an analog of the usual one, but at the very least, you know that you can do infinitesimal version with vector fields. So these two vector fields, they should translate to some specific action on this guy. And what is this guy? This is differential forms. So those two vector fields, they should give rise on the vector field on the space of differential forms, on pi T. What could that be? It should be one of the examples from before. It's not. Yeah. So I'm not saying it's super obvious, but in fact, this guy. Let's start with. Right. Yes. So partial theta. So okay, this thing implies that vector fields on R01 map into vector fields on. Is that right? Yes. On this home space. Did I write it correctly? If you have an action, generators of that, there should be a homomorphism from that to vector fields. Yeah, it's right. And this thing, remember, is just differential forms. Okay. So what do the generators mapping to? Well, the first claim is that partial theta maps to the Derang differential, and theta partial theta maps to the Euler vector field. So in fact, differential forms are functions on a space, pi Tm, and this space carries a natural action of this strange supergroup. And the generators of that, which is these kind of two innocent looking guys, they correspond precisely to the Derang differential and to the Euler vector field. I'm just claiming this, okay? Imagine that I will need to define what supergroups are and stuff like this, but by analogy with smooth things, you can at least believe that this might be true. Maybe just explain, this looks similar to the formula that we've seen before for the Euler vector field. This thing is a bit more, I don't know, less immediate to see. This thing is an odd, is it still easy to see?
So it shouldn't be difficult to like write down it in coordinates, right?
Yeah. Okay, true. But one thing that this does is this is sort of a translation because it's partial. It also changes the parity, so it should kind of move you from one coordinate to another by changing parity. So their own differential is the only thing that could be kind of. Anyway, that was more like baby, but I thought it would be a pity to not mention this. And okay, by analogy, we have some fun. So there is a definition. So we see that differential forms are global functions on this. There is a definition which says that a global functions on, if you generalize this slightly, let's say you take 2. Okay? This is some sort of space. So these are called differential norms. By moving in the alphabet. And once, if we would go to an arbitrary thing, let's say K, these are in general called differential norms. If you're interested, you can read more about them in a paper by Kohan and Pablo Chevera. Let's see.
It isn't quite standard, right? Terminology.
It is or it isn't?
It is not probably, or how
Well,
other people call it.
I only know this about this name.
Okay.
Do you think there is another name?
I don't know. I think some these Russians, Vinogradov and these people, they maybe have.
I see.
I'm not sure.
Yeah, I don't remember.
I
But
don't-
maybe it was C differential forms.
Sorry?
C differential forms.
C differential.
Well,
Z. C.
C is a curly. Because it would be its variation complex.
Okay. Okay, then let's say that this is a name for them.
So if I could kind of was trying to understand this action of the diff R01 on the home thing.
Sorry, second?
I got kind of lost trying to understand this action of the supergroup on the
Yes.
on the thing. So how do you end up with this assignment of this in this green stuff, these vector fields?
So imagine this would be like ordinary manifold stuff.
Okay.
So if you would have a manifold, then you would have a right action on the group.
Okay.
Then what does this thing tell you? It tells you that, well, in particular, if you look at the Lie algebra, so in particular, you have a map from the Lie algebra into the vector fields on M, so-called fundamental vector fields, and this is a Lie map.
Okay.
Preserve the brackets. So this thing was the same assignment. So this thing is a big group, but it's the Lie algebra of diffeomorphisms is given by vector fields, right? Vector fields are infinitesimal diffeomorphisms. So that's this thing, and this thing is just vector fields on this space. So I just wrote the same thing, but ignoring the fact that it's super.
Yes, but should I see how you end up with D for the?
Oh no, we shouldn't see it from what I said. No, that's like requires writing it, at least for me, like writing
Homework.
it down. Sorry.
Homework.
Homework, yeah, or, yeah. No. This was not supposed to be immediate. I'm just. But then you see, it needs to translate to something, and it needs to be odd because this thing was odd. So what else could it be? It's this kind of proof. Well, the other thing could be the thing you suggested because it was also odd, but that one we don't know from differential geometry, so probably they're wrong.
So is there any example of a differential form that could be familiar from?
Probably.
Yeah, Pavel had this nice paper writing down curvature and stuff, right? Using Gorms.
Yeah, I have to admit that I have not.
It's kind of cute.
Right. Yes. Okay. This is end of the fun remark. Yes. There was some stuff like this. I have yet to understand all that. But it would be, this was my place that it mentioned such a and it leads to some interesting things and observations. But the idea behind all of this kind of is that you can look at other stuff like some algebraic or like half algebraic structures, and you can sort of find some geometric meaning behind them. You can see them as functions of some generalization of manifolds and differential forms. And this is often a useful thing to do, at least for those who like geometry.
Yeah, you may like this paper, but it is by Apple only maybe on worms with the apple on the title page with the worm. And
No, that one. That
with
one.
Dennis.
That one is with Dennis. Yeah. Yeah, I was looking at it yesterday. So I recommend opening that paper.
Hopefully it is a wormless paper.
Yeah,
It is in the abstract somewhere.
yeah, I recommend looking at that paper, not looking at the first page. It has a very descriptive picture. So one takeaway message from this was that this shifted tangent bundle, it carries a natural action of this strange diffeomorphism group of the odd line. And in this way you can see that the Durham differential and this Euler vector field, they actually arise from this action. So they can be encapsulated in it.
So if we integrate those two vector fields.
Sorry?
So if we integrate those two vector fields, so the round would just with squares to zero would be just like identity plus something small, but the Euler vector field that would be something non-trivial, which is the exponential of the degree or something. Yeah.
Yes.
Yes.
Yeah.
Which is an algebra automorphism.
Yes.
I think integrating all the vector fields is more subtle.
Right.
It will close with odd time. Do you know if it's
Well, you might.
Yeah.
for us at least, the flow of an odd vector field only works only if it's non-zero. It squares to zero, so this does. And then the flow is something not super interesting. It's like identity plus linear term and something. I don't remember exactly.
Is there something? Is it easy to see that you need this homological property of it? It might be kind of natural to see that, like to have that property.
Yes. Well, I guess it depends on how you define flow.
Mm-hmm.
But we define it as an action of the outline, I guess.
Mm-hmm.
The code. And then the coordinate is homological. The coordinate vector field
Mhm.
theta there.
I see.
So
I see.
the vector field is
Okay, that makes sense. Cool, thank you. Perfect. Okay, so I think we are on a good track. Okay, so let's go back to our end of the remark, and let's get back to the section where we are. So coordinate approach to supermanifold. So remember we called about vector fields before, so now let's talk about differential forms. Might be a little confusing to do this just after telling the differential forms are functions on some manifolds, which will be true here as well, but maybe kind of try to imagine like a mental white space, vertical white space between what was said now and what I'm going to tell you now. Anyway, over done. Differential form on supermanifolds. Okay, and since we are working in coordinate approach, then if you have your supermanifold, you have some coordinates xi and xi alpha, then differential forms objects generated. This is a super algebra again, generated. Maybe we should say super algebra. Generated by these coordinates, just as we had in the ordinary case of smooth manifolds, but also the differentials. You can make this a bit more formal, but we don't need that. It just as before we were throwing in some partial symbols, now I will throw some D's. And you want to understand these things again, it's like a one object. So what is the parity of this? So this was E was even, psi was odd. But now this thing I want it to be, this thing is naturally odd because this bit is odd. This thing is even. So one kind of lore is that we care only about total parity. We care only about total parity. So sum of all parities of an object. This is a useful convention. Probably you can do it otherwise, but I find this one kind of sane. And similarly, this thing is even. This psi was odd. Okay? Also, maybe. So when I say this, we care only about, maybe too dark. Put it down. Okay. So we care only about total parity in the sense that this is what determines the commutative properties. This determines. I wonder what the sound was. Sorry. This determines the commuting properties. Okay, so for instance, if I would have like xi alpha and I would multiply this by dxi, and this is minus dxi xi alpha, because I swapped two odd objects, there's a minus. Okay, and similarly, if you want to have like dx's with dxi's, so okay, the classical example, or the usual example, you can take R11 and let's pick coordinates to be just x and xi. And then what do the differential forms look like? So there will be zero forms. Okay. Again, we define like omega p means that there is, I should say like dx or dxi appear p times. It's like a form of game. You just look at any expression consisting of these things and you count how many of these there are, and that's your degree of the form. So what are the possible zero forms of this thing? They will have no d's, right? So they will be functions. Now what functions can you have in this space? We can do this. How do we approach this problem?
Wait.
Sorry?
Wait for you to say.
Okay, so you can either have a function of t, or you can have a function of x ring, or a function of x times psi. Okay, with all such things. Let's call this collective just function of x and psi. Okay, what are the possible one forms? Well, they will start like this, so there will be some coefficient function multiplying the dx, and there will be some other coefficient function, I don't know, chi, multiplying dxi. Okay, one form. Now what are two forms? What kind of two forms can I have? So forget about the coefficient functions, there will always be function of x and xi, but what can follow those things? What are the only possible two functions? two forms that I can have.
dx dxi.
Yes, I can have dx dxi with some coefficient. No, psi. Is there something else that I can have? Exactly, I can have dxi squared. Because this is not zero. I'm not writing wedge. I mean, I could, but I'm not. Because I said that this is a superalgebra generated by these things, so it's just as good, just a formal thing of these words. You can insert wedges if you want, but you can also not insert wedges. It's just, I define it as just a formal word, it's like formal expression. Okay, so that's it. There is no dx squared because dx squared is 0 because dx is odd. Now what are the three forms that I can have? Dx dxi squared? Is there something else that I can have? Perfect. Okay, so this thing hopefully demonstrates that I can go as far as I want, so they don't terminate, so there is no top form. No top forms. In general. As long as I have any odd coordinate. Okay, so now we know what differential forms are, at least in coordinates. Again, you can make this more.
So these are not kind of defined in relation to the vector fields under supermanifold?
Well, they can be, but I'm not doing that. I'm doing the local description, and I'm just saying that it's just a game where I just use those symbols and multiply them.
Okay.
But you can do it that way, and it should give the same result.
Okay.
I mean, it gives the same result. I just wanted to, I don't know. At some point I wanted to go for kind of local anyway, so I decided this was the right time to switch from global to local description. Okay, so what is the story here? So we know that this thing is a superalgebra. Actually, I'm just saying the same thing I said. Okay, so just look at that sentence at the beginning again. We have a superalgebra of differential forms. Let me call them omega of m or curl m. And now you can imagine that we can similarly define the objects as we had before, like Lie derivatives, there are differentials, insertions, and you can again define them geometrically, just as you do in ordinary geometry. But since I haven't defined these things geometrically, let me just continue in here and just tell you what the definitions of those things are. Okay. So let me say definition. So this is kind of, if you work with supermanifolds, then it's good to have some set of conventions sometimes, if you really want to break it down, which unfortunately I was forced to do at some point. It's good to have some set of conventions, and I find the following are particularly convenient. Okay, so we now define standard differential geometric operations, and I will define them by telling you what they do on the generators. Okay, so we define the following. Derivations. Again, same definition of a derivation. It's something that is even or odd, and changes the parity, because again, this was a superalgebra, just like the algebra forms of ordinary manifold. So nothing changed there. So we define the following things. So first of all, we define D. So D is the odd derivation of omega ascending, and now prepare to be amazed. It says x to dx, xi to dxi, and it sends dx to 0 xi to 0. Okay. Since I define this thing as like a formal, you just multiply those things as you wish, and I need to tell you how this new d, not to be confused with that d, I define that as being the other d, so they actually coincide. So it's not a very intelligent thing to say, but okay, so you see, like the d in there is just a formal symbol. Now I'm defining an operator, and I define it to act like this. So you see that on the coordinates actually coincide with that d over there. Now what about the other things? This is where it gets a little bit interesting. So now for vector field that we discussed, how to describe in general, we can define L, the Lie derivative, as the derivative of parity. Now what parity should we expect this thing to be? Is it even or is it odd?
The parity of V.
Yes. It has the same parity as V. In ordinary geometry, V would be ordinary vector field, and we know that Lie derivative doesn't change to parity, so it's an even operator. Now, if V itself is odd, then it's natural to expect to set it up in this way, that it has the same parity as V. And how do we define it on the coordinates? So, okay, let me say here. So I don't. So enough to define the derivations on f and d of f. Where f is a function. So yeah, I just said the same thing, but instead of saying x and psi, I said it together. So, and okay, what I want is that if this acts on a function, then I want this thing to be simply the vector field acting on the function. And if I act with this thing on d of f, okay, maybe, okay, sorry, I think it's probably better to forget what I said here. I think it's probably, I mean, it's true, but it may be confusing to say it like this. Let's say this, where f is either x or xi. Okay. I will define this to be minus 1v on d, v acting on f. Reason is that this thing then implies that the derivative commutes with d. This is the property I want, and if you do it on, you see what this gives you a function, and you realize that this thing is a graded commutator. Which means that this thing is really LVD minus and the costal sign, where you have the LV times the D multiplying D and LV, and we know that this thing is the same as V. This thing is minus 1, and the derivative was 1. I want this property, I want this to be 0, so that gives you this formula. Okay, I wanted to, okay, anyway, this is one way to define it. Maybe it looks a bit silly and clumsy if I do it this way, but I kind of wanted to define consistently all of them on generators, so I need to do it this way. Anyway, finally, the insertion. Again, so we define I of v to be a derivation. What parity should it be? Derivation. derivation. What degree should I have now? Sorry, parity. Parity is again depending on the parity of V, but remember the insertion operator, it was decreasing, it was decreasing the degree of a form by 1. So in ordinary geometry, this I itself would have odd parity. That's why if I know now, I put V next to it, then I should add the parities. So it's this. And I define it by, well, how do you want this thing to act on functions? Well, you want it to be 0, of course, because it should decrease the form degree. And how do you define this? Well, I will define it like this. This is maybe one which is a little bit less standard compared to the literature, but I find it nicely consistent. So this thing, to make a similar remark, this thing should be read as remember as. So this is the rule where you take V, you swap it with D. See? Swap with, you're not really doing that. Imagining, you want to implement the quotient sign somehow. And one way to do it is you imagine that you first swap these guys, so you produce this sign, because D has degree 1, so there's like multiplying degree of D here. Swap them, V acting on F, and then I cancels with D. So here's the sign. It's a constant thing to do. And I believe it makes some calculations and formulas easier. So, what am I doing? Yeah, so, yeah, sure. So V swaps with D, given the Koszul sign, being Koszul sign, or Koszul. D and I cancel. This is the mnemonics for it. In either way, this thing defines how these three operators act on everything. And then let me just finish by writing the proposition. That from this, actually you don't have to remember that because it's enough typically to remember that from this you can derive the usual set of Cartan formulae. Like for instance, you can show that Lie derivative like this, maybe V, not coherent. You can show that, well, D with itself is 0. That kind of follows automatically from the definition of D. This is easy, this one you have to check, but it's easy. Lie derivatives commute. I mean, not commute. They don't commute, but they behave like this. Insertions commute. What am I missing? B with the derivative is 0. That I already used over there in the definition. And interestingly, with this one, I will comment on this one. Okay, so whatever the choice of, so the way when I practically work with these things, then I remember that there is these formulas, and then I just remember a bunch of these. I don't remember the signs, but I remember that there is this mnemonics, and I remember that they all commutes with D, and Lie derivative of function is the derivative of function, and that together determines the whole thing. So I just wanted to present it in a sort of chronological way. Now the remark I wanted to say is that, as I said, there are some choices involved. You can do some choices. You could define this without the sign. I guess that's the only place where you can make choices. Or maybe you can define. Let's not define differently than total parity. What else was the choice? Oh, yeah, you can. There was not many other choices. But anyway, the other choice, if you would, for instance, not include the sign here, then what you would have here would be this thing swapped. Okay, I'm just saying that I mean, I didn't prove the proposition either, but like, I'm saying that if you do many different choices, for instance, this one, you ignore the sign, which first you might be tempted to do it that way, then this thing would come out in the opposite way. In the ordinary geometry, this thing is the same because these things are odd operators and they anti-commute. Sorry, not they're odd. They're odd. Full stop. So it doesn't matter which order you put them. But in this case, it does matter. So if you wouldn't include this sign, then this thing would be swapped. And also these things would be swapped. So I think that this I haven't checked, but so okay, and this is maybe the last remark I want to say is that in ordinary geometry you have two formulas. This is a thing I mentioned probably before, although it wasn't really relevant. Like, you can either say this one. But you can also say it the other way around. You can say they are both true. In ordinary geometry. So this is true and the other one is true. Same as the derivative can be written either as this one or this one. Both of these, all four things are true in ordinary geometry, while in here you need to make some choices. And the choice I made, pick two of them. Pick this one and this one. This is just, if you ever find yourself doing some supergravity calculations or something, or BB or anything. It's a useful thing in life. Okay, as the last sentence I will write is that again we can view all these objects, this one, as functions, vector fields on the shifted tangent bundle, but now to the supermanifold. So you can again give a meaning to vector bundles over supermanifolds. Again, we didn't go into the details, but you can imagine doing that. And just as in the classical case, these were vector fields on that space. This thing will stay true.
I'm confused. I'm composing. Sorry. Okay. No. Dependent. No.
Okay. Okay, yeah, that's all I wanted to say about this part, and then next time we will continue. Any questions for this part? I think we can end.
So again, kind of corresponds to the left action. You insert from the left, contract from the left, right? Also, if you write v in coordinates and then you write the form, so you have to go with the partial, or not with the differentials in the form to the left, and then insert. So
Right.
That's your choice. Not for maybe the derivative, but for I and this, yeah.
So you're saying that it's kind of consistent to do it in this way, that because anyway contractions are depicted from the left.
Right.
So why not do everything from the left?
Yeah.
I agree.
If you look at different forms, manifold is supermanifold. So this is a model from R02 to something, and there is a map from R. There is a like SO circle worth of maps from R01 into R02, right?
Circle.
You can rotate the R01 into R02.
Okay, but I think there's more presumably, no? Or is it just that?
It's RP1, no?
Sorry,
Oh, yeah, sorry, yeah, this is just the linear, you're right, yeah, there is more. Oh, is there more?
I don't know.
I'm not sure now.
Okay, but
Yeah.
was there?
Does it give? But this, but I thought that this would give like a multitude of this Degan differentials, but it's probably not correct.
So in the worms and worm things, you have you have now the whole isomorphism of the biggest thing, like R0/2 or 3, I think, and you are saying there is like that, yeah, there is more
What
stuff.
is it? Yeah.
I don't remember, but there is like a lot of stuff, a lot of more. I mean, more stuff than in R01.
Okay.
Sorry, that was helpful. I don't remember. Sorry.
It's fine.
Any more questions? Comments? Complaints?
You should know by heart the work of your former supervisor.
Yes. Yes.
There are no excuses to say about it.
If differential forms are related to Hochschild cohomology, sorry, Hochschild
Is it a
homology,
Okay.
yeah. Then do you know what worms are related to?
No.
Okay.